Hi students, welcome to today's video module on Fourier series. This is a part of MSc Semester 2 Mathematical Methods in Physics, Integral Transforms. In that the first part is about Fourier series, then Fourier integral, then Fourier transform, and then Laplace transform. So here we are doing the Fourier series part 1. In this we will describe what is Fourier series and what are the conditions and a few examples of Fourier series. Okay, students? And for this, we are referring mathematical methods in physics by Afkan, Weber, and Harris. And also, we referred mathematical methods by B.D. Gupta. So, before going detailing about Fourier series, we must discuss about some historical background of Fourier series. Ancient Greek people believed that Earth is the center of universe and all other stars and planets revolve around Earth in perfectly circular paths. You can see here moon, sun, etc. revolving around Earth. But the night sky observation and other observations made by them does not match with their theoretical predictions. For example, in the case of moon and earth system, if the moon is moving in a perfectly circular path, then what is the reason for change of size or change of intensity of light? That means sometimes moon appear darker, sometimes it appear brighter, sometimes smaller, sometimes bigger. So what is the reason for this? The geocentric model proposed, or the earth as a center and the moon revolve in a perfectly circular path, that does not match with these observations. Then what they did, they consider the movement as the moon is moving in a circle, but they added one more circle to it. You can see here. So along with orbiting that, the moon is moving along another circle also, like this. But that also does not match properly. So what they did is they added one more circle with that. So by adding these circles, they modeled the earth moon system to match with the observations. Now we know that these planets, star, etc. are not moving in circular path. Instead they move in elliptical path. So you can see here sun at the focus, and then earth is moving in a circular path, I mean an elliptical path, and around that moon is moving. So that means it is like adding circles to one circle plus another circle plus another. So the Greek people, they they successfully explained the variations in many observations and night sky with this type of a modeling by adding circles with each orbits. So here you can see a circular path can be mathematically represented with the expression z is equal to r e to the power I omega t. The exponential term represents the circular moving path of that particle, and r is the amplitude, or we say the radius of the circle. Omega is the angular velocity of travel. If we add one more circle with this, you can see here the initial circle of radius r1, and now I added another circle of radius r2 with another angular frequency omega 2, and a third circle is also added with that, with a radius r3 and an angular frequency of omega 3. So adding circles as proposed by those Greek people, and that now it is they propose that without knowing the mathematical treatment or anything, but they try to explain the sky, the solar system, etc. But now we can mathematically model this by adding circles. So any number of circles we can add. So here you can see infinite number of circles are added with that. So as the previous case, R1 E I omega 1 t plus R2 E I omega 2 t plus etc etc. Or in a compact form, we can write it as sigma or summation of a minus infinity to plus infinity ck e to the power I k omega 0 t, where the c can replace the place of the radius. So in this way, we can, so there we model the movement of the planet or whatever it is with the help of this type of a mathematical model. Now, so just before going, okay, so before going to Fourier series, just watch this video also. In this video, you can see how a square wave can be represented with the help of waves, sine wave or cosine wave. They're equivalent to circular path itself. See, by increasing the, by changing, by adding more and more circles, or by adding more and more sine waves, how a sine wave just change into a square wave. In the other video, you can see another pattern is drawn with the help of circles. See how beautifully a circular movement adding circles changing to a square wave, and later you can change that to a sawtooth wave also. Here you see the head of a person is drawn with the help of a circle. See there, by changing the circles, we are changing that square wave into into a sawtooth wave now. So any type of pattern, we can, any periodic function actually, we can represent that with the help of sine waves or cosine waves. So I think you understood how we can model various situations or various patterns with the help of adding circles or adding sine waves or cosine waves. That is actually the basics or the starting point of Fourier series. Fourier series expansion is used for periodic signals to expand them in terms of their harmonics, which are sinusoidal or orthogonal to one another. Fourier series is an infinite series representation of a periodic function in terms of trigonometric sine and cosine. അപ്പോൾ ഏതൊരു പീരിയോഡിക് ഫംഗ്ഷനെയും നമുക്ക് സൈൻ അല്ലെങ്കിൽ കൊസൈൻ ഫംഗ്ഷൻസ് ഉപയോഗിച്ച് റെപ്രസെന്റ് ചെയ്യാം. ഇതിനെയാണ് ഫൊറിയർ സീരീസ് എന്ന് വിളിക്കുന്നത്. സോ വാട്ട് ഈസ് ആക്ച്വലി മെന്റ് ബൈ പീരിയോഡിക് ഫംഗ്ഷൻ? സോ പീരിയോഡിc function is a function representing a signal that repeats. Periodic function is a function that repeats after regular intervals. Examples for periodic function are sine, cosine, tangent, etc. They are all periodic functions. Okay. Here we can see Joseph Fourier, who proposed the Fourier series expansion model. In detail into Fourier series. A Fourier series is defined as an expansion of a function or representation of a function in series of sines and cosines. We saw in the case of that circular modeling of planetary system, exponential ikx, r exponentially ikx, such terms. The same thing. Here, instead of the circular model represented, we are using cos and sines. Instead of the exponential form, we are using the trigonometric form. They are also connected using the Euler equations. We know it. So the Fourier series representation of a function f of x is given by f of x equal to a0 divided by 2 plus sigma n from 1 to n a n cos nx plus sigma n equal to 1 to infinity b n sin nx. The Fourier coefficients a0, an, bn, they are related to the function f of x by an equal to 1 over pi 0 to 2 pi f of x cos nx dx. bn equal to 1 by pi 0 to 2 pi f of x sin nx dx. Here they wrote f of x just to, okay, you can write it as f of x itself, f of x dx, and here also the function f of x sin nx dx. Okay, so these are the Fourier coefficients. So Fourier series representation is f of x equal to a0 by 2 plus sigma an cos nx plus sigma bn sin nx, and an and bn are given by these expressions. It can be as I already told in the first slide, first one or two slides about the representation in exponential form. This also, see, you can see the Fourier series can be represented exponentially. F of x equal to sigma cn e to the power I n x, where cn is half an minus ibn and c of minus n is half an plus ibn. By substituting this, you will get the same expression itself, where they use the Euler formula e to the power I theta or I phi is equal to cos phi plus I sin phi. Okay, so using this, this representation of Fourier series, or in the exponential representation of Fourier series. This is what we discussed in the first two slides about addition of circles. Okay, the same thing. So we discussed the Fourier series trigonometric representation and exponential representation of Fourier series. This is the same thing. You can see f of x equal to a0. Instead of using sigma, or this is a0 by 2, a1 cos x, b1 sin x, a2 cos x, a2 cos 2x, b2 sin 2x, etc., etc., an cos nx plus bn sin nx, etc. This is what we wrote with the sigma notation. Sigma n equal to 1 to infinity an cos nx plus bn sin nx. What is an? An is 1 by pi integral minus pi to pi fx cos nx dx, and bn is equal to 1 by pi integral minus pi to pi fx sine nx dx. What is a0? You just put 0 in the an expression, you get 1 by pi sigma integral minus pi to pi fx dx. It's not necessary to use minus pi to pi every time. We can change the interval to minus L to L. This is a common integral, common intervals actually. So if you are using some other intervals like minus L to L with a period of 12, in the previous case we used minus pi to pi with an interval period of 2 pi. Here we are using minus L to L with a period of 12. So we can write the Fourier series in this limit also, a0 by 2 sigma n from 1 to infinity a n cos n. This is actually cos n 2 pi x divided by 2l. 2 cancel. That is why they wrote cos n pi x by l. In the previous expression we wrote it as cos n 2 pi x divided by 2 pi, because there the period was 2 pi. So 2 pi cancel. That is why in the first expression I wrote it as cos nx and sin nx only. Okay. So here with any general limit of minus L to L with a period 2L, we can write the Fourier series as f of x equal to a0 divided by 2 plus sigma an cos n pi x by L plus bn sin n pi x by L. So just understand how this came here. It is actually n 2 pi x divided by 2L, because the period is 2L here. To cancel and pi x by L came. Okay. And where a n equal to 1 divided by L, it was 1 by pi we used there. In general form, it is 1 by L. This is L. 1 by L integral minus L to plus L f of x cos, again, n pi x by L dx. And b of n equal to 1 by L integral minus L to plus L f of x sin n pi x by L dx. So this is a general form of Fourier series with any limits minus L to plus L. Okay. Now there are some conditions for validity of this series. For the validity of Fourier series, these are the conditions. F of x have only finite number of finite discontinuities and only a finite number of extreme values. Extreme means maximum and minimum in the given interval. What are they? What are the function? What are the conditions imposed? F of x must have finite number of finite discontinuities and finite number of extreme values. Functions satisfying these conditions are known as piecewise regular. These functions are said to be piecewise regular, and these conditions itself are known as Dirichlet conditions. Once again, the Dirichlet conditions in detail. The signal should have finite number of extreme values. That is, finite number of maxima and minima over the range explained. You can see here this function. So 0 and 2 pi. You take 0 and 2 pi here. This range. In this range, you can see finite number of maxima, finite number of minima in between this limit. So this is this satisfying the Dirichlet condition. But look at the next function here between this limit. It is an infinite number of maxima and minima occurring. So this is not satisfying the Dirichlet condition. Okay. Now, second, the signal should have a finite number of discontinuities over the range of time. See here, in a particular time interval, a finite number of ഡിസ്കണ്ടിന്യൂറ്റീസേ ഉണ്ടാവാൻ പാടുള്ളൂ. സോ ഹിയർ ഇവിടെ നോക്ക്, ഇവിടെ ഒരു ലിമിറ്റ് എടുത്തു കഴിഞ്ഞാൽ ഇവിടെ ഇത് ഡിസ്കണ്ടിന്യൂസ് ആകുന്നത് എവിടെ നിന്നാണ്? സി ഹിയർ ദ വാല്യൂ ഇറ്റ് ഈസ് ഹാവിങ് എ ഹൈ വാല്യൂ. ഇവിടെ വെച്ചിട്ട് അതിന് ഒരു ഡിസ്കണ്ടിന്യൂറ്റി സംഭവിക്കുന്നുണ്ട്, അത് 0 ആയിലേക്ക് മാറുകയാണ്. സോ there is a finite number of discontinuity in between the limit of the function. ഇതിൽ പറഞ്ഞിരിക്കുന്ന ലിമിറ്റില് ഫൈനൈറ്റ് നമ്പർ ഓഫ് ഡിസ്കണ്ടിന്യൂറ്റിയെ പാടുള്ളൂ. But you look at the first function is satisfying the Dirichlet conditions. Okay. Now second function നോക്കുക. Look at the second function. In the limit, in the proposed limit, you can see There is discontinuities. Infinite number of discontinuities are there. Finite discontinuity അല്ല അതിനകത്ത് വന്നിട്ടുള്ളത്. Infinite number of discontinuity ആണ്. So this is not satisfying. This is not satisfying the Dirichlet condition. Okay. The signal should have absolutely integrable. The signal should be absolutely integrable over the range of time period. തന്നിരിക്കുന്ന റേഞ്ചിൽ അത് integrable ആയിരിക്കണം. This function is an integrable over the time period. But you can see this is not integrable. ഇത് ഇവിടെ this is having one value and this is having another value. It is discontinuous also, and also is not integrable over the function. So the first function is obeying the Dirichlet conditions. Okay. So the conditions imposed for validity of Fourier series is that the function should have a finite number of discontinuities. It should have a finite number of maxima and minima within the limit proposed, and these conditions are known as Dirichlet conditions. Now, when we are going to learn about Fourier series, we must in detail about Fourier series, we must know what are even functions and odd functions. Even functionum odd functionum endana ennoodi manasilakiyirikanam. A function is said to be even if f of minus x is equal to f of x. If you change the variable to negative of that one, you must get the same as that of the positive value. Here you see the graph also, f of positive x. This is f of positive x. You are getting an answer. This is the answer you're getting. F of the negative, when you substitute negative, in that case also you'll get the same answer of y or the function. This is okay. So this is an even function. What is odd function? If f of minus x, f of negative x is equal to negative of f of x, it's called an odd function. Here you can see when you put f of x positive value, you will get one value of y. When you put negative value of x, you will get the same value of y, but with the negative, you are getting negative y. Here you are getting positive y as the answer. So whatever answer you got for, whatever the answer you got for f of x, you will get the negative of that answer for f of minus x. That is odd function. Okay. So this is what we learned about Fourier series. F of x equal to a0 by 2 plus sigma an cos nx plus sigma bn sin nx with a0 values, an values and bn values. These are the Fourier series and Fourier coefficients that we learned. Now let us see how these Fourier coefficients change for even functions and odd functions, or we can say this is actually some trick when you are calculating Fourier series. No need to calculate completely an cos nx and bn sin x. If you identify them as even function or odd function, then there are some shortcuts to reduce the calculation. So let us see how. We know that even function f of minus x is f of x. Examples for even function: cos x is an even function because cos of minus x, it is cos x itself. X square is an even function because when you substitute minus x square, it will become x square itself. Okay, x of sin x, I'm sorry, x sin x is an even function because, okay, before going to that, we'll learn what is an odd function. Odd function is f of minus x is equal to minus f of x. For example, x, when you substitute minus, you will get minus x. X cube, when you substitute minus, it will become minus of x cube. That is f of x is equal to x cube. F of minus x is equal to minus x whole cube. That is equal to minus of x cube. That is equal to minus of f of x. That is why. Okay, sine x is an odd function because sine of minus x is minus sine x. That is why sine of x is also odd function. Now, you consider for a this is a trick. You consider even function. You assign the symbol plus. For odd function, you assign the symbol minus. So, when you find the product, how to identify a product function as even function or odd function? It is easy to identify an a function like x square, a function like cos x, a function like x or x cube or sin x or whatever it is. If it is a single term, it is easy to find whether it is an even function or odd function. But when a function with multiples or like of the form uv product, then how to identify whether it is an even function or odd function? So for that, you assign plus sign to even function and minus sign to odd function. Then on a product uv, okay, if u is odd, then put minus. If v is also odd, put minus. When you find the product minus into minus, you will get plus. Plus stands for even in our notation, right? So the product of two odd functions give an even function. Okay. In another way, just consider u as an even function, then assign plus. V also as an even function, then assign plus. Then the product plus into plus, you'll get plus. Plus stands for even function. Then in that case, that means the product of two even functions also even. The product of two odd functions also even. Now we take in another notation, that is uv. Take u as an even function, then plus v as an odd function, minus, then plus into minus, you will get a negative. Negative stands for odd function. So the product of an even function and an odd function will result in an odd function. Okay, so I hope you got the idea how to check whether the product is an even function or an odd function. Product of two even functions is even. Product of two odd functions is odd. Product of an even and odd function is an odd function. Okay, now check the function x sine x, whether it is even or odd. We know that x is an odd function. Sine x is also an odd function. So x sine x, odd into odd, you will get an even function. So x sine x is an even function. In the same way, check x cos x. We know that x is an odd function. Cos x is an even function. So product of an odd function and an even function, it will result in an odd function. So x cos x is an odd function. Okay. Now, how to simplify our Fourier series calculations with this even and odd function representation? We know that f of x is equal to, here on the side box you can see the Fourier series and the coefficients an and bn. Now here you can see integral from minus L to plus L. We can represent it as 2 times integral from 0 to L f of x dx. And also for the odd function, integral from minus L to plus L f of x dx is equal to 0. So if f of x is an even function, if f of x is an even function, then so consider f of x is as an even function. അപ്പോൾ എങ്ങനെയാണ് a0 a and bn എല്ലാം വരിക എന്ന് നോക്കാം. a0 1, we know a0 എന്ന് പറയുന്നത് 1 by pi minus pi to pi f of x dx ആണ്. That we can write, instead of writing minus pi to plus pi, we can write 2 into 0 to pi. So that is why a0 is this function. ഇനി an എങ്ങനെ എഴുതും? an is f of x cos nx. cos nx എന്ന് പറയുന്നത് ഈവൻ ഫംഗ്ഷൻ ആണ്. ഇപ്പോൾ ഇവിടെ എഫ് ഓഫ് എക്സ് ഒരു ഈവൻ ഫംഗ്ഷൻ ആണെന്ന് കൂടി പറഞ്ഞിട്ടുണ്ട്. അപ്പോൾ ഈവൻ ഇൻറ്റു ഈവൻ, അപ്പോൾ ഈ പ്രൊഡക്റ്റ് എന്ന് പറയുന്നതും ഒരു ഈവൻ ഫംഗ്ഷൻ തന്നെ ആയിരിക്കും. ഓക്കെ, സോ അതിന് ആൻസർ ഉണ്ടാകും. എഫ് ഓഫ് എ എൻ ഇസ് ഈക്വൽ ടു 2 by pi 0 to pi എഫ് ഓഫ് എക്സ് cos nx dx. മൈനസ് പൈ ടു പൈ എന്നതിന് പകരം 2 into 0 to pi എഴുതി. ഇനി ബി എൻ അല്ലേ, വി നോ ദാറ്റ് സൈൻ nx ആണ്, ഒരു എഫ് ഓഫ് എക്സ് സൈൻ nx ആണ്. സൈൻ nx എന്ന് പറയുന്ന ഒരു ഓഡ് ഫംഗ്ഷൻ ആണ്. എഫ് ഓഫ് എക്സ് എന്ന് പറയുന്നത് ഇപ്പൊ ഈ ഒരു നോട്ടില് ഈവൻ ഫംഗ്ഷൻ ആയിട്ടാണ് എടുത്തിട്ടുള്ളത്. സോ ഈവൻ ഇൻറ്റു ഓഡ്, സോ ദിസ് പ്രൊഡക്റ്റ് വിൽ ബി ഓഡ്. അപ്പൊ ഇവിടെ നമ്മൾ പഠിച്ചിട്ടുണ്ട് ഓഡ് ഫംഗ്ഷൻ ആണ് എന്നുണ്ടെങ്കിൽ മൈനസ് എൽ ടു പ്ലസ് എൽ എഫ് എക്സ് ഡി എക്സ് എന്ന് പറയുന്നത് 0 ആണ്. You can check that one. For an odd function, negative L to plus L, f of x dx equal to 0. Any function dx equal to 0. അപ്പോൾ ഇവിടെ bn, if the function f of x is an even one, then the product of f of x sin x is also another is an odd function. Therefore, that integral will give 0. So bn will not be there. അപ്പോൾ even ആണോ odd ആണോ എന്ന് കണ്ടുപിടിക്കുക. Even function ആണ് എന്നുണ്ടെങ്കിൽ Fourier സീരീസിലെ b coefficients വരുന്ന third term ഉണ്ടായിരിക്കില്ല. So the Fourier series coefficient reduces to f of x equal to a0 by 2 plus sigma an cos nx. Now let us see what if f of x is odd. f of x odd ആണ് എന്നുണ്ടെങ്കിൽ a0 എന്താണ് വരിക? Integral 0 to pi f of x dx. But f of x odd ആണ് എന്നുണ്ടെങ്കിൽ we have learned if f of x is odd, then that integral will give 0. So a0 is 0. Similarly, an also 0. bn odd function ആണ്. Sin x bn ൽ already ഒരു sin nx ഉണ്ട്. So f of x into sin nx, both are odd. Odd into odd will give even. So integral of even. So that will be there. That function answer will be there. So bn is equal to 2 by pi 0 to pi f of x sin nx dx. So if f of x is an odd function, then the Fourier series will reduce to f of x sigma bn sin nx. a0 യുടെയും an ന്റെയും terms ഇതിനകത്ത് ഉണ്ടായിരിക്കില്ല. So these two are two tricks for reducing the calculation in case of Fourier series. So if first of all you have to identify whether the given function is an even function or an odd function. If it is an even function, you can use only a0 and an terms. If it is an odd function, you can use only bn term. The other terms will vanish. Now let us try to do one or two examples of Fourier series. Okay, so first find the Fourier series representation of a function f of x equal to x, f of x equal to x within the limit minus pi to plus pi. So how to do this one? So first of all, okay, you can see on the side box the Fourier series and the Fourier coefficients. Okay, f of x equal to a0 by 2 plus an cos nx plus bn sin nx. a0, bn and an are written there. Here function is x. We know x is an odd function because when you put minus, it will be minus of x. F of x equal to minus of f of x. So f of x is an odd function. എങ്ങനെയാണ് odd function ആണ് ചെക്ക് ചെയ്യുന്നത്? x ന്റെ നെഗറ്റീവ് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യുക. So f of minus x ഇട്ട് കൊടുത്തു കഴിഞ്ഞാൽ it will be negative x, that is minus of f of x. അതുകൊണ്ട് ഇതൊരു odd function ആണ്. Odd function ആണ് എന്നുണ്ടെങ്കിൽ we learned if it is an odd function a0 0 ആയിരിക്കും, an 0 ആയിരിക്കും. Previous slides check ചെയ്യുക. If it is an odd function a0 equal to 0 and an equal to 0, then only the b coefficient will remain. So that is bn is equal to 2 by pi sigma 0 to integral 0 to pi f of x sin nx dx. ഇവിടെ വരേണ്ടിയിരുന്നത് 1 by pi minus pi to pi എന്നാണ്. അതിന് പകരമാണ് 2 by pi into 0 to pi integration ചെയ്തിട്ടുള്ളതാണ്. f of x in x substitute ചെയ്തു. Then using the product rule, integral of u into v is u into integral v minus integral of differential of u into integral of v. Product integration of products first function into integral of second minus integral of differential of first into integral of second. In that way, x, that's first function, integral of second sin nx, integral is minus cos nx divided by n, minus integral of differential of first, that is dx by dx 1, integral of sin nx. Again continuing the integration, minus x cos nx by n first, minus dx by dx is 1, integral of sin nx is minus cos nx divided by n. Okay, again integrating this cos nx, it is sin nx divided by n. There is already one n, so n square varum. So 2 by pi minus x cos nx by n plus sin nx by n square, limit 0 to pi. Then substitute the limits. 2 by pi, ആദ്യം upper limit substitute ചെയ്യാം. എന്താണ് minus pi. So minus pi cos n pi by n plus രണ്ടാമത്തെ ടേമിന് upper limit substitute ചെയ്യുക. Sin pi Sin pi 0 ആണ്. Sin 0, 0, sin 180, 0, sin 360, 0. So in that way, sin n pi is 0. So that is why this term 0. Now substitute the lower limit. Lower limit substitute ചെയ്യാം. 0. അപ്പോൾ x ന് 0 കൊടുത്തു കഴിഞ്ഞാൽ 0 ആയിപ്പോയി. Second time sin n into 0, sin 0 വരുന്നു. That is also 0. So all these terms 0. Only one term remains, minus 2 by pi, pi cos n pi by n. Okay. Now minus, what is cos n pi? Pi cos n pi le cos n pi മാത്രം ഒന്ന് എടുക്കാം. Cos n pi is equal to 1 when n equal to 0, 2, 4, 6. Cos n pi equal to minus 1 when n equal to 1, 3, 5, etc. Or general ആയിട്ട് വേണമെങ്കിൽ cos n pi equal to minus 1 raised to n എന്ന് പറയാം. So minus 2 by pi into pi by n into minus 1 raised to n. This is the bn term. Okay. Now coming back to the Fourier series, a0 an termuകൾ ഇല്ലാതെ 0 ആയി മാറി. f of x equal to sigma n equal to 1 to infinity bn sin nx. നമുക്ക് bn ന്റെ വാല്യൂ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യാം. minus 2 by pi, pi by n minus 1 raised to n sin nx. Okay. Now summation. ഇവിടെ minus 2 by pi, pi cancel ആയി പോയി. ബാക്കി minus 2 അതിനെ common we taken outside. Then it is first one 1 is plug in the value 1 there, so minus 1 raised to 1, it is minus, then sin 1x, sin 1x. Then next is 2, minus 1 raised to 2, it is plus 1, that is why plus here, sin 2x by 2. The next is minus 1 raised to 3, so minus 1, sin 3x by 3, etc. This continues. So this is the Fourier series representation of f of x equal to x. I hope it is clear. Just try to do this from the first itself. Okay. Now let us try another example. ഇവിടെ f of x equal to x അല്ല, f of x equal to mod x ആണ്. What is the difference of what is mod x? Mod x. X, whether it is x or plus, you are taking the magnitude only. So if you substitute f of minus x, you will get minus of f, this one, that is x itself, that is f of x itself. f of minus x എന്ന് പറയുന്നത് f of x തന്നെയാണ്. Therefore here this function is an even function. f of x equal to modulus of x is an even function. നേരത്തെ f of x equal to x എന്നാണ് എടുത്തത്, അത് ഓഡ് ഫംഗ്ഷൻ ആയിട്ട് എടുത്തത്. ഇത് ഈവൻ ഫംഗ്ഷൻ ആണ്. f of x equal to minus x വരുന്നില്ല. So this is an even function. In the case of even function, we already know the trick to reduce the calculation in case of Fourier series. If f of x is even, you can drop the b coefficients. b 0 ആണ് വരിക, bn 0 വരും. അപ്പോൾ a0 and an മാത്രം കണ്ടുപിടിച്ചാൽ മതി. First of all, a0. What is a0? 1 by pi minus pi to plus pi fx dx. അതിന് പകരം you can use 2 by pi 0 to pi fx dx. fx എന്താ? Modulus of x ആണ് dx. 2 by pi x square by 2, 0 to pi. You can substitute the value about pi square minus lower limit is 0, pi square by pi. So we got pi. അപ്പോൾ a0 value pi ആണ്. ഇനി an കണ്ടുപിടിക്കണം. How to find an? 2 by pi 0 to pi fx cos nx dx. 2 by pi fx ന് പകരം x substitute cos nx dx കൊടുത്തു. Again the product rule, first function into integral of second minus integral of differential of first into integral of second. X into cos nx into differential sin nx by n minus first dx by dx is 1. Integral cos nx is minus sin nx. Integral of cos nx is sin nx by n minus. Okay. So then 2 by pi x sin x by n minus cos nx by n square 0 to pi. Then substitute the limits. നമുക്ക് ലിമിറ്റുകൾ substitute ചെയ്യാം. First upper limit pi sin n pi. But sin pi is 0. അപ്പോൾ അതുകൊണ്ട് ഈ ഒരു ടേം പോയി. The next is cos nx, that is cos n pi divided by n square. ഇവിടെ minus sign minus 0. അപ്പോൾ ലോവർ ലിമിറ്റ് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യാണ്. ഇവിടെ എക്സിന് 0 കൊടുക്കുമ്പോൾ ഈ ടേം 0 ആയിട്ട് മാറുന്നു. Then cos 0 divided by n square. Minus of minus, this become plus. So cos 0 by n square, it is 1 by n square. So 2 by pi minus cos n pi by n square plus 1 by n square. So 2 by pi n square minus cos n pi plus 1. But what is cos n pi? Cos n pi equal to 1, 0 for n equal to 0, 2, 4, etc. But 0 is already used. So therefore 2, 4, 6 is remaining. And cos n pi is equal to 1 when n is even, that is 2, 4, 6, etc. And cos n pi is equal to 0 when n equal to 1, 3, 5, etc. I mean, sorry, cos n pi equal to minus 1, cos n pi equal to minus 1 for n equal to odd. Okay. Or in general, we can plug in cos n pi equal to minus 1 raised to n. That's also a possible way. So now plug in the values. N equal to 2 by pi is there, n square, then minus cos n pi plus 1. So 1 minus 1. Okay. Minus cos n pi plus 1. So when it is even, it is minus 1 plus 1, 0. Okay. And when it is odd, it becomes minus 1 minus 1. That is minus 4 divided by pi n square. So when n is even, an value is equal to 0. And when n is an odd number, the an value is equal to plus 1 plus 1. That is plus 4 divided by pi n square. Okay, so n has value when n is equal to odd only. That is 4 divided by pi n square. We can substitute the value of an. So then f of x equal to a0 by 2 sigma an cos nx. So what is an? It is minus 4 by pi n square for n equal to 1, 3, 5, etc. For other values, we already noticed that it is 0. Okay, so the Fourier expansion is pi by 2 plus sigma n equal to 1 to infinity minus 4 by pi n square cos nx for odd values of n only. For even, there's nothing, 0. Or you can write x equal to, we can even you can expand by plugging the values of 1, 3, 5, etc. Here you will get this answer. This one also you can write as x for all values, you can write as pi by 2 plus sigma n equal to 1 to infinity minus 1 raised to n minus 1 divided by n square pi n square, I mean, cos nx for all n. ഇങ്ങനെയും എഴുതാം. ഓർഡർ ഈവൻ ഡിവിഷൻ ഇല്ലാതെ എല്ലാ എന്നിനും ഇങ്ങനെ ജനറൽ ആയിട്ടും എഴുതാം. അതിനകത്ത് തന്നെ അപ്പൊ എന്നിന്റെ വാല്യൂ ഓഡ് ആയിട്ട് വരുന്ന ഐ മീൻ ഈവൻ ആയി കഴിഞ്ഞാൽ ഫോർ എക്സാമ്പിൾ മൈനസ് 1 സ്ക്വയർ, അപ്പൊ അത് മൈനസ് പ്ലസ് 1 ആവും, 1 മൈനസ് 1 0, അങ്ങനെ അത് ഇല്ലാതെയായി പോവാണ്. അത് ഒഴിവാക്കിയിട്ടാണ് നമ്മൾ ഓൾറെഡി ഇവിടെ എഴുതിയത്. ജനറൽ ആയിട്ട് വേണമെങ്കിൽ മുകളിൽ കൊടുത്തിട്ടുള്ള റെഡ് കളർ രീതിയിലും എഴുതാവുന്നതാണ്. ഓക്കെ. So this is the Fourier series expansion of f of x equal to modulus of x. അപ്പോൾ രണ്ട് എക്സാമ്പിൾസ് നമ്മളിവിടെ ഡിസ്കസ് ചെയ്തു. കൂടുതൽ എക്സാമ്പിൾസ്, Fourier സീരീസിന്റെ കൂടുതൽ എക്സാമ്പിൾസ് അടുത്ത വീഡിയോ മോഡ്യൂളിൽ നമുക്ക് കാണാം. അപ്പോൾ ഇപ്പോൾ ഈ മോഡ്യൂളിൽ Fourier സീരീസ് എന്താണെന്നും എങ്ങനെയാണ് Fourier സീരീസ് കണ്ടുപിടിക്കുന്നത്, ഈവൻ ഫംഗ്ഷൻ, ഓഡ് ഫംഗ്ഷൻ, അതെല്ലാം വന്നു കഴിഞ്ഞാൽ ഏത് രീതിയിൽ Fourier സീരീസ് സിംപ്ലിഫൈ ചെയ്യാം, ഇതെല്ലാമാണ് നമ്മൾ ഡിസ്കസ് ചെയ്തത്. So we have discussed about Fourier series and how to calculate Fourier series for even function and odd function separately, and we discussed two examples also. More examples will be discussed in the next video module. Okay students, bye, thank you.